Hello everyone, again welcome back to the latest lecture session. So we have been discussing remediation of soils and sediments. In that context we are looking at solidification and stabilization, right. So let's dig right in now. So we talked about solidification and stabilization. So what are the major aspects or players that we have here, right. So obviously we need to have solidification, right, solidification typically improving the physical properties, and then stabilization, right, making the contaminant immobile or even less toxic, let us say. So obviously in this context, solidification, we are trying to bind the relevant material, let us say. So what do we need? We need a binder now, right, we need a binder now, yes. So what are the what do we say kinds of binders that we have? We are going to look at that. So again the binder is such that let us say it is going to improve the physical characteristics of the waste when it is mixed with, let us say, water and the waste, let us say. So binder, water and waste will form a particular mixture that improves the physical strength, let us say. And obviously we are also going to have looking at admixtures, right. Typically binders are added in relatively high fractions, let us say, right, and admixtures in very low fractions or content, and these are used, let us say, to make the compound less toxic or degrade the compound while it is within this matrix or such, right. So again solidification and stabilization, and typically we need to add a binder, and obviously we will depending on the type of contaminant you will also maybe add a admixture now, right. So what are some of the binders that we look at? Obviously, right, so to improve the strength or physical strength of a particular slurry, let us say, you have water and you have this contaminant and you have other matter out there, and you want to improve the strength of this material or this slurry, pardon me. So what will you add? You will add a binder. And what kind of binders do we typically have? We have, let us say, cement, obviously, right. So cement, how does that work? Obviously, so you have you typically have, let us say, when cement hardens, calcium silica and hydrate complex or CSH complex is formed, right, calcium silica and hydrate complex, CSH, and that is the matrix that imparts strength to this particular concrete, let us say, right, or hardened cement, pardon me. So let us just look at what we have here. So here let us say we have different types of cement, right. First let us say if we talk about composition, let us say, this is typical what do we say formula for cement. So here we have tricalcium, right, and we can also have dicalcium as in CaO2, SiO2, right, and also calcium silica and aluminum or calcium silica and iron, right. You can have different types of these particular elements in there, but typically we are almost always going to have C and S or calcium and silica, right. So once you add them to water, let us say, right, what is going to happen? So add this particular cement, this is cement as you see, the tricalcium, right, to water, you end up forming this CSH matrix, right, calcium silica hydrate, right. So CSH matrix, and obviously again CaOH2 is given out. Obviously what will this do? It will increase the pH. So that is something that we will have to look at or consider later, but keep that in mind that when we add cement, right, to water, we are going to have this particular hydration, and this hydrate CSH matrix form, right. So you are going to have this CSH matrix form, right. So other than cement, what are some of the other what do we say materials that you can maybe think of that can act as a binder now, right. So typically we are looking at improving the physical strength, right. So what's one substitute for cement that you can typically think of, let us say, that can end up or leading to formation of again the CSH matrix now. So obviously we can think of fly ash, right. So you have different types of coal, and in thermal power plants, let us say, when you burn this particular coal you have the relevant ash, and that is typically we have the relevant fly ash here, right. So again in fly ash what do we have? What is this rich in? It is typically rich in silica, let us say. Fly ash is typically rich in the silica content, let us say, right. So to form the CSH matrix, what do you need? You still need the calcium, let us say, right. So you can add some lime or calcium in the form of lime, right, or let us say depending upon the type of fly ash, you will also maybe have some lime inherent in that fly ash. So, pardon me, depending upon the type of coal, so we have type F coal and type C coal, okay. So, different levels of purity, right. So, type F coal typically has less CaOH, let us say, right, and typically type C has more calcium, right. Obviously, both will be rich in the silica content, right. So, in this type F where the calcium content is less and in type C where calcium content is more, obviously in type F, right, you will need to have or add lime, let us say, right. Why is that? Obviously, you need a source of calcium, right, because you already have S and you need to add calcium, right, and then water obviously and CSH matrix, right, that is how it is going to be formed. Type C, you need not maybe add calcium because you already might have significant or considerably or sufficient calcium in your particular fly ash there, right. So, again that is something else, or as we looked at, if I am adding both cement and fly ash, where can I get the source of this particular calcium? As you see from the hydration of cement, you release this particular calcium hydroxide, and that again can act as source of calcium for the fly ash here. Let us look at the relevant reactions here. So, here I have let us say fly ash, right, and I add calcium, right, and then again what do you end up forming it? CSH matrix here, right. So, again CSH matrix, right, and again people look at slag from again blast furnace and such and so on, right, but there are different binders. So, typically though people look at cement and fly ash, right. So, that is something to keep in mind, and what are we trying to form typically? The CSH matrix now, right, that imparts the strength more or less. And how is this particular contaminant going to be transformed? Let us say there are different ways, but typically let us say it can be adsorbed onto this particular matrix, let us say, I think it is called a Tringite substitution, right, or it can precipitate out, let us say precipitation reactions can occur, complexation reactions can occur, right. Complexation, I think we have metal and ligand and so on and so forth. So, you supply the relevant ligand and you are going to have complexation, right, and you have maybe degradation too, depending upon or reduction, pardon me, let us say, or oxidation depending upon the type of admixture you add and so on and so forth. So, what do we look at? We need to look at adding the relevant binder and if required the relevant admixture and so on and so forth. So, let us look at some of the other aspects, right. So, solidification and stabilization, what is it now? Binding agent is typically your cement, fly ash and so on. We have some other binders, but these are the binders typically used again. So, contaminant media or waste, so obviously can be done in situ, right, by injecting the binder into the contaminant media, or it can also be done ex situ by excavating the materials and then mixing them with the relevant agent and off site or such and then disposing them. Again, keep in mind that let us say if you have hazardous waste slurry, you can't directly dump it in a landfill because there are certain regulations again even for the kind of waste that you can dump in a landfill with respect to their leachability or such, let us say, right. So, that is something typically to my knowledge ex situ is more widely practiced, in situ not a lot, but we will look at the relevant data. I think we have a decent schematic later on. Right. So, here what are the different types of binder materials now, right. So, we have some organic binders, but typically we end up using a lot of inorganic binders, and that is something that you can see. Again the source is US EPA, right, Environmental Protection Agency. So, we have inorganic binders typically as you see the fraction or which are the major fraction of the binders that are typically used. So, you have a combination of inorganic and organic binders. This is sometimes used to promote let us say adsorption, if I can say so, and also degradation. For degradation you obviously need an electron acceptor and a donor. So, if one of this is missing, let us say the organic compound can act as that, let us say, depending upon the type of compound, and only organic binders, but that is relatively rarely used as you can see. Organic binders, what do you see? Obviously activated carbon, asphalt and different types of clay, and inorganic binders which form majority of the binders let us say are cement, fly ash and lime. Obviously, you might need lime in conjunction with fly ash. Phosphate again, which can either lead to precipitation let us say of the relevant what do we say compound, or adsorption let us say, or even complexation, and soluble silicates or sulfur, relatively less widely applicable, let us say phosphates, sulfates and sulfur and silicates and so on, right. But typically cement, fly ash and lime, and typically as you can see they are the most popular or widely popular binders. So, one other what do we say way of solidification and stabilization is vitrification. Though I do have that as an alternate solidification and stabilization treatment process. So, typically there are two kinds, let us say. What are they? Two kinds of solidification stabilization. Cementitious, or where I am adding cement or trying to form the CSH matrix, and the other one is vitrification, right. And what is this vitrification about? It more or less is like you provide enough heat, let us say, that the sand, let us say, that you have in your particular mixture, let us say, is going to melt, and then once it cools down it is going to form a kind of a glassy material, and as it cools down it is going to encapsulate, let us say, right, encapsulate, pardon me, everything that is within that particular study. So, what do you need? Obviously you need sand, and you are going to apply considerable amount of heat, let us say, and you are going to melt the sand, and while it hardens, cools down and hardens, you are going to have a glassy kind of material form that is going to encapsulate all the relevant contaminants. But obviously you need to put in considerably high concentrations of your considerably high temperatures. So, thus your cost is going to be relatively high, and application is typically for, let us say, radioactive waste and so on and so forth. Let us look at some of the other aspects. So, here obviously can be ex situ or in situ, but typically vitrification is a good choice if ex situ is not feasible and you are looking at in situ techniques, right. You need a heat source, can electric current, direct fired kiln, typically used in situ, right. And then obviously as we say, it is not I do say soil here, it is typically sand, right, typically sand, pardon me, at high temperatures. As you can see, you need to maintain or achieve pretty high temperatures, right. So, it immobilizes most inorganics, and depending upon the type of organic pollutants, they can be destroyed by pyrolysis, right, lysis, right. And inorganics, as I mentioned, will be incorporated within the vitrified glass. As this particular mass cools down, you are going to have that incorporated within it, right. Organic pyrolysis combustion products, if they are volatile or such, an off gas treatment needs to be required, right. And so, again depending upon the site conditions and depending upon type of contaminant, you can go for vitrification, right. So, let us move on. So, different types of sites that we have typically what do we say, remediated by solidification and stabilization, right. So, let us look at what they are. Manufacturing gas plants widely in India, maybe because it is relatively less industrialized, maybe not a lot, but yes. So, but in India we face this a lot, wood preserving sites, let us say, right, or wood treatment sites and so on. Certainly industrial and municipal landfills, that is a great aspect. Military bases too, because of the type of ammunition or the firing ranges that you have, let us say, typically we find applications of solidification and stabilization plants there in the military bases and the ammunition plants. Certainly oil recycling facilities or even electroplating facilities or industries where you have heavy metals, let us say contaminating the relevant soil, plating facilities, and oil refineries and battery disposal, again heavy metals and so on, right. So, what are the typical contaminants that people try to remediate, right? What are they? Typically metals, mostly metals, and we have lead, arsenic and chromium leading the list, but obviously depending upon type of heavy metal, you can have most heavy metals, let us say, or if you have a site like Moradabad, the one that we discussed when we were looking at excavation, right. What did we have? People were trying to extract heavy metals from this e-waste, right, and you now have a soil contaminated at relatively high concentrations with different kinds of what do we say, or different heavy metals, right. So, in that case obviously what is one pretty decent way to go about remediating that particular site? It is solidification and stabilization. As in, I believe that the regional officer there did ask me, let us say, what are the relevant options, such that he can't put in a lot of money, he can't really see to it that heavy machinery comes in or such, or remarkably heavy machinery comes in, or ex situ is not a great option for him, right. He wanted something in situ. So, in that context, maybe solidification and stabilization is one particularly good way to go about things, right. Again, more on that later. So, organic contaminants, let us say, typically petroleum products and byproducts during distillation and so on, right. So, again different contaminants and sites. So, as you see, the effectiveness obviously of solidification and stabilization depends upon the kind of the soil or the media and the type of contaminant. Let us look at what we have here. So, we have here that this is from the technology performance review, again typically EPA or ITRC publish these, right. So, selecting and using solidification stabilization treatment for remediation, let us say. So, you can look at these technology documents, let us say, to be able to understand the applicability of your particular or applicability of solidification stabilization, pardon me, to your particular site, right. So, we have let us say cases where the effectiveness was already demonstrated, and also cases where no effectiveness is expected, and where let us say it is not yet been demonstrated, but we have literature available through research, let us say, that says it is a potential candidate. So, let us look at the demonstrated effectiveness, and obviously as we discussed earlier, for inorganics, right, it is widely used and demonstrated. So, non-volatile or for metals and radioactive materials, solidification stabilization is a great way to go about remediating a contaminated site. Obviously depends upon the extent of contamination, the depth, and so on and so forth, right. So, for let us say again for PCBs, right, PCBs again we have a lot of them in contaminating the relevant Moradabad site, PCB again from e-waste. So, again a good way or good particular technique there for remediating the soil would be solidification and stabilization. Why is that? We have a wide variety, and we have heavy metals, we have PCBs, and so on and so forth. And even for sites with pesticides, I think we have a case study coming later on, and semi-volatiles or non-volatiles, obviously it should be relatively non-volatile or semi-volatile, right. So, relatively less to no efficiency, let us say, would be for volatile compounds, right, and maybe for dioxins again present at your particular Moradabad site, its potential effectiveness, but depending upon the binder and such, we need to obviously understand the relevant site before being able to what do we say, confirm or deny such effectiveness, let us say, right. So, again what do we have? Typically for metals pretty good, for PCBs also pretty good, right, and obviously for volatile compounds which would prefer to stay in the gaseous phase rather than in the aqueous phase or the solid, not solid, pardon me, aqueous phase, let us say. Obviously you want to have solidification stabilization is not a great way to go about it, right. So, let us move on. So, here this is one good document, not document, pardon me, a picture or pie chart I want to look at. So, here we have source control treatment technologies again from EPA or the relevant technology performance review, right, selecting and using solidification stabilization treatment for site remediation. So, first let us understand that ex situ technologies and in situ technologies. Typically ex situ are relatively more favored and in situ relatively less, but still they are both neck and neck. And within ex situ, as you see, there are a lot of them, but as you can see a majority of it would be by solidification and stabilization within ex situ. Even within in situ we will have solidification and stabilization, as you can see, but relatively less what do we say, widely used or adopted now, right. Since we are looking at this particular pictures, also let us try to look at some of the other aspects that we have already looked at. For example, bioremediation is looked at for 5%, let us say, again obviously within in situ. Chemical treatment and such, we are going to look at that later. So, let me not come back to that here, right. What else have we looked at? Let us say again obviously one is solidification and stabilization and so on. Again bioremediation off site, again relatively less percentage, right. So, again as we can see, typically we see that solidification and stabilization is remarkably widely used. Look at the what do we say, its preeminence here. All the others are at maximum is 11% here, right, and I think more or less that is it, maximum is more or less that. Soil vapor extraction, as we discussed in terms of in the context of natural attenuation, we are going to discuss this later again, soil vapor extraction, right. So, obviously if the compound is relatively more volatile, then you can go with soil vapor extraction and such. That is obviously again an in situ technique, right. So, that we are going to come back to that. So, solidification and stabilization remarkably widely used, right. So, let us move on. So, here we are just going to look at a few sites or a couple of sites and then move on to relatively more detail with respect to the how to go about solidification and stabilization and work out a particular practical problem, and then we look at a few case studies. But for now let us say we will just look at a couple of sites, pardon me, to understand what goes on. So, here we have a Superfund site. Superfund is how they classify based on the level of cleanup required, let us say. In the US, they classify some sites as Superfund sites. Anyway, a peak oil Superfund site in Florida, right, again ex situ soil mixing at peak oil site, right, ex situ anyway. So, what do we have here? So, it was formerly a waste oil recycling plant, and here we have an area of 15.5 acres, right. And then again, as is the case with such sites, you have the site contaminated with a wide variety of contaminants. What are they? PCB, heavy metal, phthalates, plasticizers, and contaminated ash too, right. So, we have different kinds of what do we say compounds here or contaminants. So, what is the treatment method that they have followed, let us say, or the remediation technique, pardon me. So, they excavate the soil and then also backfill or put back some decent or uncontaminated soil, let us say, to a height of 8 to 12 inches, 1 inch 12 inches means I guess it is 1 foot above the water table with clean soil. First they excavate the soil to that particular contaminated zone, and then put back, let us say, not put back, put in fresh soil, uncontaminated soil, so that it does not obviously disturb the groundwater table, I guess. So, that is why they are putting it to such an extent that it is 1 foot above the water table, and then excavated soil blended and treated with granules to immobilize the lead, okay. And then again this is an admixture, right, and then resulting material was mixed with cement, which is your binder, in a mill, pug mill more or less, right. And what is the volume? As you can see, 19,000 cubic yard, let us say 1 yard is approximately a meter. So, 19,300 meter cube, considerable volume again, right. So, let us move on. So, here we have another site, redevelopment project in Massachusetts, right. Again, why did I choose these sites? I guess just to give an overview, let us say we are going to look at case studies, but typically I did not find enough data in the Indian context, that is why we are looking at these sites anyway, right. So, now we have a manufacturing gas plant, and that is around 10 acres, right, and byproducts, right, again with petroleum residues. And what was the temporary cleanup? This is something that we discussed earlier. It was capping the subsurface, right, they capped it, right. For example, let us say they just capped it as in containment, they are just trying to contain the what do we say contaminant. They do not want the contaminant to be transported over a wider area. So, the temporary cleanup remedy was just capping the contamination, right, and that was in place for 30 years looks like. And then after the relevant investigation, they found that 4 acres of soil was contaminated for up to 20 feet, right. 1 foot is around 12 inches, right. 3 feet is typically what do we say 1 meter, right. So, here we have almost 7 or 6 meters deep contaminated zone here, right. Aromatic hydrocarbons, volatile organic carbons, and also a 3 acre NaPl, right. This is something we looked at, non-aqueous phase liquid in the context of your groundwater contamination. So, again they had a DNaPl at groundwater and clay interface for about 20 feet, and LNaPl on groundwater surface around 10 feet below the grade, right. So, DNaPl is the dense non-aqueous phase liquid. So, obviously that is why you would expect it to go further down, and LNaPl is relatively lighter. So, that is why it is at relatively the higher not elevation here compared to the DNaPl, it is at a higher location, right. So, that is what we have here. Let us see what people have done, right. So, excavation and disposal outside NaPl, and in situ solidification and stabilization to treat the NaPl plume and contaminated soil, right. So, excavation and disposal for the outside the NaPl, for NaPl outside the property, pardon me, and in situ to treat the NaPl plume and the contaminated soil, right. So, that NaPl that they could capture, they were trying to excavate that and take that out, and the contaminated plume where NaPl is already throughout your particular has been relatively diluted, but has spread over a wider extent. Obviously, as you know, pumping and treating it out or such is an issue, maybe bioremediation could have been carried out. So, but they went for solidification and stabilization in situ though, right. So, what else have they been up to? So, what did they look at? They looked at Portland cement, bentonite clay, and water is injected. So, thus immobilizing the NaPl in the subsurface. So, what did they do? Cement, clay and water, right, again trying to solidify more or less, and thus obviously in this process of solidification you are also stabilizing the relevant material, which is NaPl in the subsurface, right. And how they do that? Obviously, as you can see here, this is a picture from the relevant site using a 10-foot crane mounted auger system. You know the auger system, I guess, right. And based on that, while churning it, and they also injected the relevant binder here, right. So, what do we have here? We have immobilization of contaminants up to a 10-foot thick monolithic solidified mass. It is monolithic now, right, up to 20 feet, and then volume, as you can see, is almost 1 lakh meter cube, right. That is a remarkably high volume, as you can see. It is almost equal to 1 lakh meter cube, based on our information that 1 yard is more or less equal to meter, right, 1 lakh meter cube. So, you understand the extent of sites that are remediated or are typically remediated by your particular solidification and stabilization, right. So, let us move on. So, what are the aspects that affect the cost of this solidification and stabilization? Obviously, the site, the bigger the site, obviously, you know, it is going to be affect the relevant costs. The type of contaminant, based on the type of contaminant, right, you will also have to choose whether it is feasible for in situ or you need to go for ex situ. But obviously, as you have seen in the relevant pie chart, most of the times we have to go for ex situ though, right. So, site contaminants and ex situ or in situ, they obviously play a role. So, if it is ex situ treatment, it is used to treat excavated soil. So, you are going to take out this soil to a particular off site location, and then, you know, add the relevant admixture or binder and then treat it and dispose. So, and then again the operation and maintenance obviously depends upon the rate at which you can process your particular system, let us say, or the contaminated media now, and obviously the volume of soil. As we saw earlier, I think we looked at 10 to the power of 5 meter cubes of soil. That is more or less an average, not average, let us say slightly above average volume of soil to be treated, let us see. Obviously, site and type of contaminants, right, and site meaning that more or less we typically look at the amount of binder that is to be added here, right. So, here what are the major cost drivers for ex situ? So, if the moisture content is relatively high, you know, that is an issue, right. The greater the moisture content, let us say, the greater the relevant what do we say, treated material is going to be more permeable, and also the greater the chances that, let us say, your contaminant is more mobile and such. So, moisture content is an issue. Type of contaminant, because then you will need to choose your admixtures accordingly, and also the size of your particular system. But for example, let us say for 100 cubic yards, let us say when I say small scale treatment, it depends upon 100 cubic yard, let us say, or 1000 meter cube, that we are classifying as small scale treatment. Large scale is 50,000 meter cube, around 50,000. So, as you can see, the costs are around $125, so into 70 rupees now maybe, or 75 per meter cube, right, to depending upon the site, obviously again, right, we have $70 per meter cube. I guess it is the matter of scale, that is why the cost is slightly coming down for large scale treatment per unit, but obviously the total cost is obviously going to increase, right. So, let us move on. So, what else do we have in situ treatment though? Typically we use augers or injector systems, and nowadays India, we have our particular systems are construction techniques or such are pretty advanced, you know. So, these kinds of construction techniques or pieces of equipment are not an issue. So, we use augers or injector systems for mixing, and then reagents are applied through nozzles. Again, this we looked at maybe in the context of PRB, when, or the permeable reactive barrier, when we were injecting I believe fine slurry of zero valent iron into the subsurface, right. Reagents can be applied through nozzles at the bottom of the augers while the mixing is done with the soil, right. Or again grout injection, we will not go into that in great detail. So, obviously treatment costs in situ, what do they depend upon? Project size, and what are the characteristics of the relevant soil, again moisture content and so on and so forth, the type of the contaminant again, and thus additives or reagents used and so on. So, for in situ, what are the costs? Obviously, as you see, the costs are relatively lower, but only when they are shallow applications. But when they are deeper, obviously different kinds of techniques need to be used, and thus as you see, the cost is relatively high. So, it depends upon the type of subsurface or the subsurface soil characteristics and the extent to which or the depth to which the contamination has taken place, right. So, with that, I guess I will end today's session because we are running out of time. So, in next session, let us say we are going to look at some of the more technical aspects that we need to consider when looking at solidification and stabilization. As in, let us say I have a particular waste and I have the waste to be contaminated with many heavy metals, let us say. How do I know which pH to maintain? Because typically at particular pH, the solubility of these heavy metals is less, right. So I need to maintain a high enough pH such that even when I conduct the TCLP test on this waste, the heavy metals will not leach out, let us say. But as we know, at one particular pH, right, there is no one particular pH at which all the heavy metals are going to be pretty low. So it is a balancing act. So you need to first choose the pH, and then you need to also define, depending upon that, you need to look at how much cement to add, how much fly ash to add, how much water to add, and how much of the waste, I guess, the fractions of these, right. So we are going to look at those calculations and so on, and I guess with that I will end today's session, and thank you.